Transient current. The term transient represents the variability. You see, whenever the cell or any source is switched on, the current will start increasing gradually. It will take some finite value, but will start from 0. Thus, after switching on or after switching off, the current is always variable. The growth and decay both the processes are exponential, and the time taken in the process of growth or decay of current depends on time constant that is given by L upon R. This is known as time constant. You try to find out the dimension, you will have the dimension T. You see, a circuit has been shown over here. In this circuit, if you press the key and cell is allowed to work, the final current is going to be the maximum current, that will be E upon R, because you see L here is functional as coil only during the variability of the current. When the change in the current stops, means it attains the maximum value. In that case, the coil becomes simply a connecting wire, and the maximum current that will be possible here is equal to E upon R. Suppose you start the key, current will become maximum this value, but it will take some time. T second after starting the circuit, the value of current could be given by the relation, it is given over here. Means this is going to be exponential. It could be plotted this way. This is the maximum current I and T. Now, if you put the value T equal to tau, means you want to find the current after tau itself, that is time constant. It is going to be 1 minus 1 upon E, and interestingly, if you solve it, you will find this thing. Means time constant is the time after which current becomes 63%, 63.6 almost, it is given over here, 63.6% of the maximum current, that is known as time constant. If you try to find out the rate of change in current and you differentiate this, you will find this result, di upon dt equal to R by R, di dt, this is equal to R by L I naught minus I. You see, it is going to be maximum only when I becomes 0. In that case, this is into I naught, and I naught is equal to E by R. So, you could say the value of di dt maximum, that is highest rate of change in current, is given by E upon L itself. Similarly, when you switch off the circuit, the current will start decreasing exponential. This is given as the relation. T second after the current will be given by this relation. Graph would be like this for decrease of current, and di dt will be given by the relation minus R upon L into I. Let us see oscillatory current. The two currents I told you, increasing and decreasing current, after switching on and after switching off. Oscillatory current means you have a charged condenser, you connect it with a coil, condenser was initially charged. Condenser will get discharged through the coil, and soon as it is about to be discharged completely, it will start getting charged because of induction, and this process, the whole process will continue, because you see it is the nature of the coil. When the current will start decreasing, some induced current will be produced in the same direction. When the current will start increasing, some induced current will be produced in the opposite direction. That is why oscillatory current is going to be produced this way. this is theoretical, but mathematically I could explain this way, that you see this E induced EMF, that could be written as Q upon C, this is given as L di dt. Second law, Faraday's, E equal to minus L di dt. Then you can say here this 1 upon L C Q, this is di dt. Another step higher, you are going to get this result d2i dt2 equal to minus 1 upon LC, dq dt is going to be I. You see, this is very interesting. This is the relation just like d2x dt2 equal to minus omega square x. You must remember, this is a very important equation of simple harmonic motion, or you might say oscillation. The two equations are quite parallel to each other, confirming this omega square is replacing 1 by L C, and moreover it is also establishing that the current produced here is oscillatory in nature. This oscillatory current is going to have the frequency given by the relation 1 upon root L C. You see, now is the time to compare the quantities that we came across in this chapter with the mechanics. So, we have put equations of mechanics here in this side and that in the electromagnetism here, and we have established the analogy with momentum and flux, this force, EMF, mass with the self inductance, velocity with the current, and this displacement with the charge. These are analogous to each other in the two branches.